Hello, economics on today. I'm going to finish up a discussion of chapter 5 with my co-leader with the statistical school and correlation negative expansion and negative. Start off with a joke. My residuals and I have a lot in common. No matter how hard we try to move on, we keep dragging the past into the future. So today we're going to primarily focus on serial correlation detection, correction. Textbook also covered a little bit about generalized least squares. Serial correlation, the word serial means sequential or continuing on. Correlation means to join. And another word for serial correlation is autocorrection. The height of the people in a population would most likely be random. If you're looking at the height. So the height of person A to person B are not likely related. However, if you're going to look at a genealogical line of your ancestors, where each individual contributed to the genetic profile of the next generation, you would expect to be some form of serial correlation. The height of you is related to the height of your parents, and your parents' height is related to the height of their parents. And you often see serial correlation in things like in economics. You can find it in places like when you look at GDP, inflation, stock returns. You can see serial correlation in finance and weather forecasting. Really, anytime you have a time series analysis where sequential patterns can exist when data is related from one to the next. The thing looks kind of like a P, I think it's called rho, if I remember right. It's an autocorrelation coefficient. And it's where the error terms are related to each other. So that's why it's connected to the error there. And then the VT, they're essentially uncorrelated homoscedasticity. That's the random noise that occurs within a model. If we don't really account for serial correlation where it does exist, the problem is that we'll end up underestimating the variance of errors. And that can result in underestimating the standard errors of coefficients. You can't, which could also result in incorrect estimation of the coefficients. It might result in inflating the t-statistics for some or even all of the coefficients. Let's look at how we detect it. We can detect it by examining the residuals. And so I've got a data set here, and we have this model. It is looking at airline tickets or airline passengers through time. I don't know if these are hundreds of thousands or thousands. These are number of passengers, and we have a date. So I added a column called time, and then there's, depending what quarter it is. And when we look at these coefficients, we can see it's a pretty strong R squared. The F test is really fairly significant. When we look at these terms through time, there are more and more passengers. Every time period. Now, this is monthly data, even though I have these quarter dummy variable as monthly data. Every month, there's 2.66 units of passengers in increase, is what this model suggests. And we're assuming a linear relationship. We're running a linear regression. If we look at these quarters, quarter one is the base quarter. And so it looks like the fourth quarter of this data set is the least amount of traveling. Most travel is the third quarter on the airlines. And of note, this data is from 1949 to 1960. I'm sure this time would be a little bit different. The constant increase of travel, and when I think about the GDP per capita of the United States, it has increased substantially, especially post World War II. There's a huge amount of economic growth. And the fact that the time variable is positive, that would seem to suggest that airline travel might be a normal good. As income goes up, people travel more. And back in the time period of what this covers, a lot of vacationers would often go to state parks or things that are nearby where they live. I think if we had more recent data, you would see substantially higher amounts of travel than what number of passengers than what we see today. So there's a little bit about our data set. Well, let's look at the error terms. We can do that by mapping these out. get the two mixed up. I think we look at this one first. Oh, we don't want the y variable in there. Okay. Let me make sure that this is right before. Okay, that is right. I'm going to anchor these, or we'll anchor these plus that. We want to get the error term, the number of passengers minus y hat. And so everything after C2, that's the estimation of y hat based off of the model. We have an error of 41. I'm going to drop this all the way down by double clicking. And when I do this, I'm going to come down here where it says sum, and that should be 0. I must have done this right. So we have these error terms. Let's see if these error terms are related to each other. I'm going to drop this into a scatter plot. And it almost looks like a bunch of random noise. It may not be so much of a linear distribution. It's kind of got this U thing. Looking at just plain a scatter plot might be a little bit more difficult to identify if one residual is related to the next one. So I'm going to turn it over to a line graph. And there we can see if it was random, you would see a lot more up and down. There is some up and down, but it does somewhat appear that each of these residuals, the last one residual is related to the residual that's before it. So graphically, because we see this pattern of these numbers that are closely to each other, I'll bring back the problem. Because, like, for example, these are all together, and then there almost seems to be a pattern within the residuals where one residual is connected to each of these residuals are connected to each other in a pattern instead of just being random white noise. That would seem to suggest that you might have some of the serial correlation. We can also do a regression analysis on the residuals. And you note that when you do this, you estimate the estimate value of one residual is related to the previous residual, means they're connected to each other. And if this row is significant, then serial correlation exists. And you note that there's no 0 with intercepting this. So I'm going to run a regression on the residuals. And we should be able to see something in here. So let's see. And actually, I'll do one more thing. I'm going to lag the error terms. Okay. And let's add one more. So here. Let's add one more error term up. These are just lags of the error. And so that's, for example, in period 3, we can see what the error term was from 2 terms above. I'm going to do 2 different ones. Let's see. Let's do this 1 and then 2. Let's switch one better. Click on the data and this is correction. Okay, my y variable. The x variable is going to be right next to it. 5 and don't have labels, set the constant to 0 and drop this right here. Okay, let's see what happens. So when I start to look at these things, I notice that the coefficient for the row is 0.367. Is it significant? Yeah, it's quite significant. So we've detected some serial correlation. But what happens if we look at, let's look at a higher order. So we just look at one error. Maybe there's additional structure. I'm going to add this one. It has a 2 lag. And Look at that. These are both significant. And so which means that there is a pattern within the pattern as well. And if we do an F test on this, which I put right over here, we have an F test value of 5.25, critical about 4, projected null. So the full model is better than the restricted model that we. And so there is evidence here that we do have some serial correlation. Another way we can do this is something called the Durbin-Watson statistic. And we calculate, we sum with the error terms. And then we also look at I think, let's see. We look at this model, we're looking at the error term minus the lag one, the square all of that, divided by the error term squared. And then you go to the table and there's a low, Durbin-Watson low, Durbin-Watson, or lower and upper, and then 4 minus upper. As long as it's between, if the Durbin-Watson figure that you calculate is right here, it's positive serial correlation. Right here, it's a significant negative serial correlation. It's right here. If the value Durbin-Watson statistic is right there, it's not significant. And here it's going to be indeterminate. And let's take a look at we have for our data set. So the last few columns are 4. We have 2 error terms. The difference of the error term squared. And because we're squaring it, that doesn't matter. It means lag versus sine. Let's get the error squared. Calculate the Durbin-Watson. It equals sum of 2 divided by we have maximum 11. So all of the error terms divided by the lag 1 squared, we got divided by the error. Okay. And so make sure we pull out my textbook, I think at page 381. And we have, how many observations do we have? For this model, there are 142. So it's going to be closer. Well, or the table has 100 and 200. And so I'm going to put the values in 1.654, 1.694. But we have 1.252, which is well below the lower value. And so we have significant positive. And when I set this up, I just put a VLOOKUP over here so that they can give us what the results are. Therefore, we do have significant positive serial correlation based off of the Durbin-Watson statistic. That's the Durbin-Watson statistic. Let's look at the next one. So we look at the Durbin H. Durbin H. And something to point out, the Durbin H, like the Durbin-Watson statistic, the Durbin H only tests the first autocorrelation of the residuals. In fact, we use the Durbin-Watson statistic in the model when we're calculating this. I'm going to go to our data set. We have Durbin H. And let's see, I'll take a little shortcut because we have this already. Oh no, the model is a little bit different. Okay, so we have our Spanner regression. With a Durbin H, you add a lag of the Y variable. And so I have this this extra value here, the passenger flag one. So I'm gonna run the regression on here. Data. Okay, we have as our y variable passengers. We have it's constant. Not being down here. Actually, I'm gonna do one more thing. I'm gonna tell it to give the residual plots. No, the residuals. Then I don't have to do any of that. Okay. And there's the predicted y and the residuals. So if I want to make it easy, there's the residuals from the top of this all the way down. Then I'll check where it says sum. Okay, yeah, so it's 0. So those are all my residuals. Let's look at the lag value of them, which we need. We want to calculate the these okay. It's like so calculate our Durbin Watson. We need to difference these, square the difference of these. And we need to square this as well. Squared. Okay. So the Durbin Watson is going to be sum k divided by L. Durbin Watson 1.7. That's a little bit different. That's going to be a higher number than what we had here. So our Durbin Watson was 1.252. And the reason why this comes out differently is because we've added this passenger lag variable. And so I think it probably looks like a lot of the persistence is captured, persistence of serial correlation will all be captured by the lag variable. Okay, the standard error of y1. So we have, these are our variables right here. I'm going to copy these and I'm just going to pop them right here. A special. And so the standard error of y1 is going to be that there. And the variance is just like that, the standard error squared. We have 143 observations. So the Durbin H, plug in that formula, you end up with 1.772. And because these are normally distributed with the mean at 0 and 1, I'm going to use a 1.96 value. So if that's great, in this we reject the null, and at least with this model, when we calculate the Durbin H, there isn't serial correlation, but notice that this model is a little bit different with that extra passenger lag is right. There's our Durbin H. What about, oh, you can also do time series analysis on the residuals. We have another chapter on time series, and we do cover this a little bit in later chapters, but you could take whole courses on time series analysis. And if you're trying to detect serial correlation, you're looking where things are related to each other, then you'll have that relationship with the previous error terms, and it's a little bit beyond the scope of this particular course, but that is another way to detect serial correlation. How do we fix it? Let's look at the Cochrane-Orcutt method. And I'm going to, let's see, go to, I have a whole tab. We have to work on this. So I estimated our model we did before. And well, we can run a regression on these, but there's another formula we can use in here that Excel provides. The formula is called slope. And you want to see, so the known y's the known x's. And you notice we get this 3.76. We come back here. That's the same value that we have right here when we calculated the slope. That's the row or the serial correlation coefficient. Another way you can do this is the line estimator formula. We have our known y's. We have our known x's. We want it to be, let's see, false or zero. You can do false or zero. We want it to be set the intercept to zero. And look, we get the same value. So those are a couple of tools that you can calculate this. I'm going to set this thing right here to this value, at least this value initially. We can adjust it. And in here, we want to calculate, so we calculated the row, the serial correlation coefficient. We want to have a new y star and then our x stars. So y star is the y from before minus the lag value of the y with our serial correlation coefficient. And then you estimate a model. A y star is your intercept, and then you all your x values. And then you have an estimate of the estimate. Now, I think in our textbook, we have extra hats on these things. And that's the way to treat for serial correlation. Let's go ahead and build up our model. So we have, so our y is going to be that minus the lag of y times the serial correlation coefficient. I'm going to anchor the serial correlation coefficient. You run it all the way over here. Okay, that looks good. Got track the first thing to go there. Looks I have that. And the one thing we'll do a little bit different is when we calculate the error here, the error is not off the model, but rather it's off of what the actual data set is. I'm gonna put this in here. We'll nice to use matrix algebra to calculate. Oh, it's Econometrics. Less clicky, but we'll do that. Let's set this off. This is our y estimate. That's the y estimate from this. And we're going to take that minus. So now we have our estimated error term. We'll drop that down. It won't equal to zero because it's not off of the y star. And then here, it's going to lag it. And then when I want to run, we'll run this regression and with this correction, you want to do a reiteration. If you're reiterating, instead of running the regression over and over again, we're going to use this line estimator equation. That way we can automatically do the regression. If this is the copy orca, this is an iterative process. And so I put this on here, line est with the y variables in column K, the x variables columns L through O. And we do want to intercept. And I guess you can show the stats or not. 1 or 0. If you don't, well, Okay, and with the line estimator, it throws everything backwards or whatever. Oh, probably because it has these extra statistics down here. But anyways, so they don't get confused with intercept, I guess, or whatever reason, line intercept is backward. But we have these on here. And now that we have these, we have a new set of intercepts. Now that we have this model, what we'll want to do is, oh, I didn't do this there. We fix this. The error term is the intercept, anchor that plus time plus quarter two plus quarter three plus quarter four. There's our estimate. And let's come back over here, passenger minus what y hat 6 weeks. That gives us our error term. And now when we calculate the row value, we come up here where it says data analysis, regression. Our row value is based off the error term. So there's our error one, and our lagged errors is that constant is 0. And we'll drop this here. And we have now our coefficient, which is going to be 0.960289. And now we need to keep doing this over and over again until our coefficients don't change. Because it's all set up and the regression remembers everything. It's just really automated. We can keep running through it until the variable changes. And you notice with each iterative process, the we end up getting the coefficients change less and less and less. And you keep going, and don't get change. You keep going until they quit changing. But it's really easy just to click on data analysis, hit enter a couple of times. Oh, they're not changing it. Okay, we converge onto this correlation coefficient of 0.999 and 213 with this model. So that is the Cochrane ORCUT. We can also look at the Hildreth-Lewis. The Hildreth-Lewis is sort of similar. But in this one, you're trying to minimize the sum of squared errors. So we have our model over here, and we'll do our Y star just like we did over here. I'm going to copy this to see if it sets. Okay, yeah, so there's our Y star, copy these down. The Cochrane ORCUT model is related to the Hildreth-Lewis. That's the Cochrane ORCUT also. We haven't been substantial right there. Go back to past data. If we're going to estimate, we're going to use the same. We end up with our model again. Let's look at where the error term is, error squared. We're going to look at the sum of squared errors of the model. There's our error. I'm gonna drag this all the way down. Okay. So we estimate our error, and sum of squared error is going to be sum. And if we put in different values of this, oh, that's right, we wanted the error squared. And we can put in different values and this will change. I'm going to set this equal to right here with the convenience solver to minimize the sum of square error. I'm going to come up here, set objective. Let's take that. We want to take the minimum value by changing the zero correlation coefficient. Solve. And after a minute, and now we have this adjusted to based off of the minimum sum of square error. That's their Hill method correction. Great. Well, that's what I have for you today. I hope this was helpful in understanding something about the serial